Thank you very much for the nice introduction. Good morning, everyone. Thank you very much also to the organizer for giving me the opportunity to present a bit of my research to this wonderful conference. So my name is Sonia Mahmoudi. I am now based in Tohoku University in Sendai, also an affiliated member of this center. And so basically today I'd like to talk a bit about actually a research project I've been doing like 3 years ago during my PhD, and hopefully it will be a bit interested for a broad audience. So yes, and this work was joint work with my supervisor, Professor Motoko Kotani, and also Dr. Munisuke Fukuda from also Tohoku University. So let me give a bit of first general introduction and motivation behind this work. So if you were already here in the winter school last December, so I will just, of course, repeat a bit about the introduction, but it's always nice to get some review. So exactly 10 years ago, actually, I was doing textile engineering in Taiwan. So it has been like a long way from textile engineering to mathematics and not theory, but it's also very nice to see like all the connection we can have between the different disciplines. And so at the time, it was like really product engineering and trying like to find some appropriate textile structure having specific function. And when I came back to academia and doing mathematics, one of the first questions I wanted to have is like really trying to think about this bridge, this connection between these different fields. So was like, okay, when we think about textile, as first we can think about our clothes. We have two main ways of creating textile, which is using weaving technique or knitting techniques, which are like completely different and which will really have like different mechanical property. And I'm sure you heard a lot from Sabeta in different of our talks. And actually, recently, like all of these techniques have gain like a really broad interest outside of the classical textile industry, since we are now talking about weaving like molecules or weaving carbon nanotube, like to get very like multi-hierarchical and multifunctional type of new materials or structure. And so we have a very like important let's say need from different fields to get a better understanding of all the mathematics and the topologies that we can find behind the structure, as it appears that a lot of the physical properties can be really linked to this topological one. And I think this is one of the things we study a lot in this center. So, and what's a very interesting point is that we're really talking about techniques that exist like from thousands of years, since we know how to weave and to knit for a while, and even like the very new and sophisticated machine like are still more or less reproducing like the same techniques that we are using a long time ago. And despite this long-term existence, we still don't have like a full understanding and a more universal idea or mathematical model to get a good understanding of this property. So I started my PhD with this main target of having a better understanding of the topological property of textile, and particularly weaving at the beginning. And then more recently, it has been a bit broader, considering that, for example, in chemistry, we have many structures called like polycatenan, which also have a lot of interest. So it was trying to think that many of the textile structure or other pattern we can find in chemistry sometimes will display like periodicity. So I had some focus on these patterns that will be doubly periodic in the plane. I will explain a bit more. So when we think about this connection between topology like mathematics and physical or mechanical property of object material, it might be a bit abstract. So I always like to give this very simple example, still using traditional textile as some kind of toy model just to get an intuition. So basically, if we compare the three most basic weaving patterns that are called a plain weave, when all the strands are going exactly 1 times over, 1 times under, like repeating in that way. The twill weave, which has a particularity of having some crossing organized in the diagonal way, like in these patterns. And finally, the satin weave, when we have a lot of jump, like for example, the thread will go like 4 times over and only 1 times under, and so on, going in these repeating patterns. We know by experience that the property of the material will be different from easy mechanical property to like more sophisticated properties that I could not even explain right now. But the idea is trying to get a better understanding and intuition about how the topology, like thinking that we are not changing the material, we are still using the same yarn. It doesn't matter at this stage if it is satin or polyester or any other type of material, but still get these different properties. So trying to have this general idea that if we have a better understanding of this structure-function relationship in the future, whatever the field, chemistry, textile, or whatever, we will be able like to predict the function we would like to attribute to some material during the design process. So yeah, that would be like the big picture and the big idea, like to have this kind of software in the future when we could do not only design, but also like simulation to get material with a desired property. And obviously it will be relevant in the context of this center, thinking about sustainability instead of like just continuing the trial and error process we are used to. Okay, so we understood that basically we want to understand the relation between topological structure and physical properties. So one possible starting point is first to analyze the topology from a mathematical point of view. So as I was saying, here we are talking about structure that are most likely like almost two-dimensional and that will display periodicity in 2 directions. So we are talking about like patterns that repeat in the XY, let's say, axes. So small, easy reminder about basic unknown theory, because this is the foundation of all this research. So you might be familiar with the fact that we are trying to understand if 2 3D knotted structure could be the same or not. Like that can be one of the main questions, and then classify them and try to distinguish them in terms of different parameters to characterize their complexity. And when we talk about classical knot theory, we are talking about closed curve, which are like intertwined, let's say knotted with one curve knotted itself, or multiple curves which are interlinked. And one approach and one way of thinking and analyzing this object is to simplify a 3D problem into a 2-dimensional problem. To simplify first this, let's say, the degree of complexity. So you might be familiar that we will represent, we will have a 2D representation of the knot in the plane with this kind of like crossings that will mark the over-under information, representing which part of the yarn or the strand will be over the other. And there have been like this really nice tool, or let's say like characterization of trying to answer the question if 2 knots are the same or not, which was characterized in this theorem, which was stated by a Reidemaster, which will say like if we can deform a knot into the other, so we are talking about equivalence through continuous deformation. So to answer this question in 3D, we can manipulate the 2D object with very small, simple local deformation. And if by a sequence of this move we can get from knot to the other, then we can answer that they are equivalents. And here it happens that these 2 knots can be actually completely undone to become the unknot, and this could be proved going slowly to all this small move. But obviously you don't want to do that for this kind of complex knot and just doing a move after the other. So there will be like some tools that we call invariants that are created to let's say, answer more or less in a simpler way if two knots will be the same or not. Okay, so this was the basic knot theory, like talking about object in our physical space. And mathematicians have been interested into studying knots in other spaces which will have some more or less constraints. So one in which we have been very interested was a knot in the torus. So we are talking about curves that are knotted and winding around the torus, and we will still have the 2D representation with this over and under crossing, this time on the surface of our donuts. And here, one of the main differences, and I really want to highlight this point because this will be a key step in the result I will present after, is that we were saying that here in 3D we were talking about knotted curves that are closed. And here it is the same story, but when we are in the torus, we will have two types of different closed curve. We will have the curve that will be contractible in the surface, so they will not wind around the whole of the torus, and they can just like recontract into a point. And we have the other curves that we call, so okay, the first one we call them nullomotopic, and the second one essential, meaning that they will wind a certain number of times around the longitude and the meridian of the torus. And that would be a very interesting thing. And why this torus is interested in our case, remember we were talking about these periodic patterns, and it happens that if you have a knot or a link in a torus, you could cut the torus along the longitude and the meridian, and you will obtain a flat pattern that then you can tile along like the two direction, and you get your two periodic structure. So of course, when we talk about topological characterization, we're interested in the same question. If we have two patterns, if we have two woven patterns, a woven knitting pattern, or whatever these doubly periodic patterns, we want to classify them, to compare them, to say if they are the same or not, to say if they can be a knotted, maybe we will, this is something like a pattern we would like to have complex knotted structures that could then fall apart, or on the opposite, this could be something we don't want to achieve in some experiments. So these are the questions that we also, of course, want to answer in this kind of context. And obviously, like there were like mathematicians a few years ago who also started being interested into this question. So it was a very beautiful collaboration between textile engineer and researcher, and also mathematician to also try to answer this question. And one of the approach was to consider still our 3D, quasi 2D objects that we can project very easily in the plane and have this kind of diagrammatic 2D representation. And then instead of studying like the full complex patterns, since it has periodicity, obviously we are more interested into studying the small patterns on the level of a unit cell, which when we identify the opposite side, ends up in this knotted structure in a torus, as I was talking before. And the approach we choose to use was an inverse approach. So this time we start from knot and link in the torus, and then we go to this doubly periodic tiling. And one of the reasons and motivation behind that was that we already have a very strong and good background on knot theory in the torus, so it was like a good starting point to start from things we already know and manage quite well to go to more unknown things. So, okay, I already explained that. We choose a longitude and a meridian, we cut along, and we tile our plane to get these doubly periodic patterns. And remember, we were talking about deformation. So obviously, when we do some kind of local deformation, if I take a strand and I twist it or untwist it, if I take a strand that I push on the top or on the bottom of another, as it happens on the level of this knotted structure on the torus, once we duplicate, once we tile whatever the size we want to tile, the deformation will repeat also along the two directions. So here is an example of the original one and the deformed patterns, which where the periodicity will be preserved. That was a condition we chose to keep. And that is, so far, if we stop here, we can say, okay, we can use everything we know from classical knot theory, and we can understand some deformation happening on the periodic level. But then it happens that when you want to compare two periodic patterns, you just want to make sure you don't forget anyone, let's say, in the equation. And it happens that just studying this local deformation that are already well known in classical knot theory won't be enough. And so we want to consider what are the other possibilities from different patterns to obtain equivalent doubly periodic pattern, let's say, from what equivalence relation can we get from patterns on the level, let's say, of a unit cell. And here is a very simple example. If I take this doubly periodic woven patterns, which is simple because it is alternating in the sense that each line going exactly 1 times up and 1 times down and repeating, you can obviously say that if I take this blue big unit cell or this red or pink one, you just have different unit cells for the same pattern. So there must be an equivalence relation between them, which was not already, of course, like a thing used in classical knot theory because we were not comparing different, let's say, unit cell of the same periodic patterns. So here is a very classical roadmap to go from, let's say, this big blue pattern to a very small pink patterns. And it happened that, of course, duplicating or like having a change of basis in your point lattice are all different tools you can get to obtain an equivalence relation between all of this knot or link in the torus. So these are like having a good choice of pattern is very important, and depending on the application, you might be interested in finding a specific cell, a specific size of your unit cell. In mathematics, we're interested in finding the smallest cell possible for some kind of classification problem, but for experiments, you might have an interest into choosing like different size. So this is a very important point to take into consideration. And as I was showing, and here is just a small announcement about a poster that is presented in the backside of this room, is that the work I have showed before was a way to think about a 3D problem into a 2D, using a 2D approach, but another way is to stay in 3D, and I also wanted to share that we have also a very nice tool, and this is part of a collaboration with Yuka Kotori, Sabeta Matsumoto, and Kenichi Yoshida here today, in which we are also analyzing this relation of equivalence from, saying, in a 3D perspective. So I'm sure Yoshida-san could tell you also more in the poster if you still have the chance to see it. Okay, so basically we had an understanding that there were like other things that the local deformation to take into consideration, and here can be the different choice of bases in the same lattice, which would be explained on the level of a torus as having some full twist of the torus, and that could give an equivalence relation between here, the pattern number 1 and the pattern number 2. That would actually explain just a shearing here of the knitting pattern. So this is kind of very beautiful idea to describe a complex periodic problem into like a more smaller problem, let's say, on the level of the torus. And the second one, we already talked about it. It's the relation between like different tiling of the same patterns that could describe eventually like contraction and extension of the full pattern here. If we see it, I could say more later. Okay, so now I still have half of the time to tell you more about the main result I'd like to show today. So remember that we were talking about having eventually in the future some more like computational tool to get a better understanding and modeling these patterns. So here is one approach. It doesn't need a lot of technical tool in mathematics, but it's still like it can be quite useful. So here, what the idea was to find some relation between classical tiling tessellation of the plane, which are like very basic, and this kind of like doubly periodic knotted or tangled patterns. And I'd like to say that the idea of this work actually came from a very nice discussion I had with our next speaker, Professor Koya Shimokawa. So when I was a PhD student, I had the chance to discuss with Professor Shimokawa quite a lot, and he could tell you obviously more about this research, but there were like this idea of trying to understand the topology of some structures that appear in chemistry. And one of the possibilities was to consider this connection between classical polyhedra, like the Platon or Archimedean polyhedra, and to use them as a scaffold to like entangle some kind of strands and create some knotted structure here. And so it was quite interesting. I've been very curious about this. This bridge we had between like classical and simple, let's say, polyhedra and this linked structure. So I've been more like into like the detail of the team that was presenting this construction method. And so here are the three references. So this team presented three ways, let's say, to create this kind of polyhedral link starting from a polyhedra. And one of the first methods here is called cross-curved and M-twisted double line covering. So you have a polyhedra, and of course we can describe that the polyhedra with edges and vertices. And depending on the degree of the vertices, you will have this kind of rule when you will get a curve going. So here, if you start from this way, you are going 2 times clockwise here to get this orange patterns. In the blue one is going counterclockwise from this one to this one. And anyway, you have a rule to kind of draw your strands on the locally around the vertex. And then each of the edge of the polyhedra will be replaced either, so here by 2 lines that can twist a certain number of times. So that was one method. Then we have a similar one that is called the branch curve, and this time you are going from one edge and you are branching directly to the next adjacent one to get this kind of patterns. And same, you replace the edge by twisted or untwisted double line. And the last one is only in the case when you have a vertex of degree 4, when you can replace each of the edge by just single line, and you make them cross over or under at the vertex. So here is an example of this polyhedral link, starting from a classical cube. And here are different examples using the method A, which is cross curve, with 0 twisting, 1 twisting, or 2 twisting. And so that was quite interesting. I was looking at this, and then I was going into Wikipedia to learn more about solid, and I ended up in this really nice part when you have this relation between the classical Platonic solid and doubly periodic tessellation of the plane. And I was, okay, so if we can do that for the polyhedra, we could basically use exactly the same method, this time for tessellation. And so I started drawing a lot, just printing many classical tessellation of the plane and using the same method we have seen before. And I was like, oh, cool, I see my weaving appearing here, but I'm not seeing only weaving, I'm also seeing patterns like this one when we have close components that could be thought of this kind of polycatenan structure. So I was like, okay, in which case we will obtain open curve or closed curve? That became the question I wanted to answer. So the same method we have seen before can be applied to a planar graph, and we can obtain the different type of doubly periodic entangled patterns as we have seen before. So here's just a simple example with a square graph. And as we were saying before, when I introduced this topic of doubly periodic structure, it was not only about studying like the full periodic patterns, but trying to reduce the problem on the level of a single cell, a unit cell, which can be seen. So here in the context of a tiling, we will obtain a graph in the torus. And so here is an example. If you just take one unit cell of these periodic patterns, I choose here the B method, branch curve, and one twist here, and then having our tiling. So it works pretty well, obviously. Then there were like this mathematical description, which being a bit more formal. So, you know, we like to use definition, theorem, and proof type of presentation. So I won't get into the detail. It's just to show you that it exists. And the main idea here was to consider that replacing each edge by these lines that will eventually twist together can be done considering the edge outside of the neighborhood of the vertex to have a good description of this process. And then also explaining what happened on the neighborhood of the vertex when this line are going on the top or of each other and following the method like the specific path that's happening. So here, for the vertex, it will happen around the neighborhood of the vertex. Okay, so we end up having formalized this different methodology, and as we say, like as I was saying, like when I was making my first drawing, like just using, for example, the simple graph, simple square graph, and using the 3 method, it happens that we will get some patterns which look like weaving patterns, which are just open curve, like following, of course, certain rules, but the yarns are open yarns as we are doing when we are creating textile. And sometimes we will get rings that are intertwined with each other. So that was this question of trying to understand in which case I will obtain one of the patterns, the weaving patterns, or the polycatenan patterns, or mixed patterns. So at the time I was not doing knitting, but now of course we could also eventually, maybe there were some specific rules to get knitting from this methodology. Of course, there might be this question to not only stay in our classical 3D space, but to think also about other space. And it happened that the methodology, if there are some mathematicians interested into the hyperbolic space or also higher genus surfaces in this audience, I just also wanted to share that obviously these methods also work for graph in the hyperbolic plane when we can also obtain this periodic entangled structure in H2. So that was just a parenthesis. And so now I will just take the 5 last minutes to answer the question, how can we predict if we start from a graph and if we choose one of the 3 methods, if we will obtain open curve component or closed curve component? So as we were saying before, here we need to study this not on the level of the infinite periodic patterns, but about what's happening in the torus. And remember, around the first slide, when I show you the difference between classical knot in the space and then knot in the torus, I told you that we have 2 different types of curve around the torus. We have the contractible one, and we have the ones which are not contractible, and that wind around the whole of the torus, a certain number of times around the longitude and the meridian. So this was exactly what happens. So here, if we think about, for example, the creation of these patterns, we start from here, these triangular patterns, right? And we apply this method. So when we apply this method, what we are doing is as we are using the graph as a scaffold, we are saying that our strands should follow a specific path, and we are walking around this graph. And so what we are interested in here is not necessarily in these nice ending patterns, but in following what path is walked around the graph. Because if we know which is the direction we walk around the graph, we will be able to understand if at the end we walk a path that can be contractible or a path that will wind around the torus. So that is the main idea here. So when we see that on the level of the periodic patterns, only one component here as an example to get an open curve would be, one possibility is to do this zigzag around the edge of the triangle, and another one would be, for example, to create this closed loop. And so then this is only one component, and we can imagine that there will be many of them intertwined together. Okay, so here we want to know if the curve will be open and closed, but we want to get this answer on the level of the torus. So having a good understanding about this path that is worked to, so each of the three methods, we could say, for example, that the method, here it was method C, one single line crossing on the top or each other when we have a vertex of degree 4, we can say that once we arrive at on the neighborhood of the vertex, we will go counterclockwise to the second counterclockwise edge to continue our path. So you see, we are just defining the walk that we are doing in our graph, saying that we are going into an edge, we arrive at a vertex, and what is the direction at which level we turn left or right, let's say, as we will be driving into our graph. And so we end up having a description of going left, right in our torus. And this is quite interesting at the end because we can use some algebra here of the torus here, saying that if we touch the longitude of the meridian, so here that are model using the alpha and beta curve. So here, for example, if we say that we go around E1, so the arrow is pointing in the positive direction. If we go the other way, we will go into the negative direction. So here, let's say, like if we are pointing here, here, and here, we are obviously seeing with our eyes that we are doing, let's say, an open curve, which will be like a non-contractible curve in the torus. And we could describe that we are working like to E1 and then E2 and then again E1 with a positive direction. So in any case, I will conclude as my time is up, but the main idea behind that is to say, what do we need to get a weaving? What do we need to get a polycatenan? Or what do we need if we want some curve to be open or closed, depending of the result we want to get? And try to have an understanding that on the torus, how are we walking around the different edges and which paths can be characterized? So here is an example. So for here, we have two examples with these patterns. I give an example of a path that will give you closed component, and I give you another example that will give you open curve. So the main message here is that we can understand if we will get open or closed component at the end, just looking at a small algebraic description with symbol that will characterize the different edges we are walking around in the graph. So that is the main point I wanted to share with you today. From a graph and a choice of methodology, we can predict if we will get closed or open component to obtain the kind of pattern we wish to get. So that's all for the research part, and I'm just very happy to let you know that also we will have this summer joint symposium with WPIS KCM Square, also related to this topic. So if you are around Sendai, it will be in Sendai, Japan, the last week of June. We will have experts from different fields, mathematicians, physicists, chemists, discussing the relation between these different patterns and potential property. And there will be also a special issue from the journal Mathematics, which will not only be mathematics, but also all the application we could think of. So that will be, also maybe not a proceeding, but it would be some kind of, we are very happy to get some papers related to this topic. So, and if you have any interest into many of the related works on periodic structure, textile, and from a mathematical perspective, I'm also happy to share. Yes. all the literature that is close to. So thank you very much for your attention.